Very well. Chapter 11, power series. So what we learned so far? In chapter 10, we start talking about sequences. Then we define new objects series. Review. In chapter 10, we said that, okay, suppose you have a function, f of n equals to a sub n, a sub 1, comma, a sub 2, comma, a sub 3, and so on. And you say that, okay, you can form a new object and we call it a sequence. Remember that the domain of the sequence, the domain is equal to n natural numbers, so it doesn't include left-hand side of your graph. We say that a sequence is convergent if the limit of an while n goes to infinity is equal to a constant unique number like L. Then you say that we have the convergence, convergence sequence. F of n equals to a sub . Then we started taking the terms of a sequence and we formed something new, a new object that we call a series. We add the terms of a sequence like this, a sub 1 plus a sub 2 plus a sub 3 plus the rest of them, and we form a new object, a series. The sum a sub n starts from 1 goes to infinity. The series. We say that a series is convergent if the partial sums S sub n, which form a new sequence, is a convergent sequence. So partial sums, if partial sums is a convergent sequence, then we say that our series sum a sub n starts from 1 goes to infinity is convergent series. Then we start talking about different types of series and techniques in understanding the behavior of series. Series. We define the geometric series. Then we define the p-series. We talked about alternating series. We talked about harmonic series. Then we went over different techniques of understanding the behavior of series. We can compare two series, an less than equals to bn, series an less than equals to series bn. We said that, okay, if the smaller series is divergent, so as the bigger series, and if the bigger series is convergent, so as the smaller series. We talked about the limit comparison series. We say that if it's equal to a constant like c, and c is positive, then both of these series are convergent or both of them are divergent. We talked about integral test, 1 to infinity of an, which was f of n. Now we work with function f of x dx. And we said that if this improper integral is convergent, then you say that your series is convergent as well. We also talked about the ratio test and root test. For ratio test, we said that the limit of absolute value of an plus 1 divided by an while n goes to infinity. If this is equal to L is just a number, and L is less than 1, then you have an absolutely convergent series. And we know that any absolutely convergent series is also convergent. So we say that our series is convergent. Today we're going to talk about a new types of series. We call them power series. Power series is defined this way. It has the form sum C sub n times x minus a raised to n starts from 1, goes to infinity. C sub n is constant, some numbers, some coefficients. A is also a constant, some numbers, some coefficient, and n ranges between 1 to infinity. Very well. We say that a power series is convergent on an interval. How do we find that interval? We use the ratio test to find that interval. So we say that x, absolute value of x minus a, the distance between x and a is less than r, the radius of convergence. So r is called the radius of convergence. Okay, let us go over one example to see what's going on, how we can apply the ratio test to find the radius of convergence. Take a look at this example. Let sigma -1 raised to n, x to n, divided by square root of n plus 1, n starts from 1, goes to infinity, be a power series. So the question says, find the radius of convergence. Find the radius of convergence. Okay, what are we going to do? We're going to start using the ratio test. We use ratio test to find r, or the radius of convergence. So remember the ratio test. The ratio test was the limit of absolute value of an plus 1 divided by an, while n goes to infinity. So your an is the whole general term for your series. So an plus 1. It means that whenever we see n, we're going to add 1 to it. We get the limit of absolute value, -1 raised to n plus 1 times x raised to n plus 1 divided by square root of n plus 1 plus 1, divided by -1 raised to n times x to the n divided by square root of n plus 1, while n goes to infinity. Okay, since you have -1 to n plus 1, it means that we can rewrite this as -1 raised to n times -1 raised to 1. And since you have x raised to n plus 1, you can split this and write it as x to the n times x. Now you can get rid of common factors. -1 to the n, -1 to the n. x to the n, x to the n. So this limit is now equals to the limit of absolute value of -1 times x. If you flip your denominator, you get square root of n plus 1 divided by square root of n plus 2, while n goes to infinity. While n goes to infinity, the speed at which these two terms are going to infinity are the same. So this limit is just equal to absolute value of -1 is 1. It's equal to absolute value of x So this is your limit. There you go. Remember that the ratio test says if the limit of absolute value of an plus 1 divided by an while n goes to infinity is L and L is less than 1, then you say that you have absolutely convergent series or a convergent series. Okay. So this is your L. If L is less than 1, then you have an absolutely convergent series. So as you can see, absolute value of x is less than, or the radius of convergence is 1. So on the interval -1 to 1, your series is convergent. Another example for you. Suppose I change my power series into -3 to the n. -3 to the n. Let's see what changes we see here. So as usual, question says find the radius of convergence. What are we looking for? We're looking for R. Okay, we're going to use a ratio test like before. Ratio test says you have the limit of absolute value of an plus 1 divided by an, while n goes to. This is the limit of absolute value of -3 raised to n plus 1 times x raised to n plus 1 divided by square root of n plus 1 divided by -3 to the n x to the n divided by square root of n plus 1 while n goes to infinity. There you go. Again, we can rewrite this limit as the limit of absolute value of -3 to the n times -3 x to the n times x divided by square root of n plus 2. The whole thing is divided by -3 to the n times x to the n divided by square root of n plus 1 and n goes to infinity. So let's get rid of common terms, -3 to the n, -3 to the n, x to the n, x to the n, and while n goes to infinity, square root of n plus 1 divided by square root of n plus 2, they cancel out. The limit is equal to 1. So this guy is equal to absolute value of -3 times x, which is 3 times absolute value of x. This is your L. The whole thing is equal to L. And if L is less than 1, based on ratio test, we know that we have an absolutely convergent series. Okay, what do we have here? We have 3 times absolute value of x less than 1. If I divide both sides by 3, I get absolute value of x less than a third. So r is equal to 1 over 3. So in this case, the interval of convergence is negative a third to a third. Interval of convergence. Over this interval, this power series is absolutely convergence and also convergence. Well, we define a power series and it is a function. So since it's a function, you're allowed to take the derivative, take the integral of your power series. So a power series is a function depends on x. So Cn x minus a to the n starts from 0, goes to infinity. So since it's a function, we can differentiate this function. Okay, let me write this function in expanded form, then I start taking the derivative. If I plug in 0, I get c sub 0, x minus a to the 0, c sub 1, x minus a to the first power, plus c sub 2, x minus a to the second power, c sub 3, x minus a to the third power, plus the rest of the terms. For f of x, can be written as this is just 1, c sub 0 plus c sub 1, x minus a plus c sub 2, x minus a squared, c sub 3, x minus a to the third, c sub 4, x minus a to the fourth, plus the rest of the terms. Okay, let us start taking the derivatives of this function. The first derivative of this function, f1 of x is equal to the derivative of constant is 0 plus the derivative of c1 x minus a is c1 plus the derivative of the third term is 2c sub 2 x minus a plus the derivative of fourth term is 3c sub 3 x minus a to the second plus the derivative of this term 4c sub 4 x minus a to the third power plus the rest of the terms. The second derivative of the function is equal. The derivative of 0 is 0. The derivative of constant is 0 plus the derivative of 2c times x minus a is 2c2 plus the derivative of 3c3 x minus a to the second power is 2 times 3 times c sub 3 x minus a plus this derivative is equal to 3 times 4 c sub 4 x minus a to the second power plus the rest of the terms. The third derivative of the function is equal to, okay, the derivative of 0 is 0, the derivative of 0 is 0, the derivative of constant is 0 plus 2 times 3c sub 3, 2 times 3c sub 3 plus 3 times 4 times 2, because we have exponent 2, we have to drop the original exponent, 2 times 3 times 4, C4, x minus a to the first power, and so on. So you can continue this process. If you continue this process and take the nth derivative of the function, you get some terms left. So notice that the first derivative of the function, at a, if you plug in a, all these terms are going to be 0. The only term left is constant c sub 1. The second derivative of the function at a, second derivative of the function, if you plug in a, it is 0, this is 0. The only thing is left is 2 times c sub 2. The third derivative of the function at a is equal to, so all of these terms are 0 except for the constant 2 times 3 c sub 2. 2 times 3 c sub 2. If you continue this process, the nth derivative of the function at a is equal to n factorial c sub n. So this is your first derivative. This is your second derivative. The third derivative, and this is the nth derivative of the function. Nth derivative. So now you have a nice formula for c sub n. Wherever you see c sub n, you can replace it by the nth derivative of the function at a divided by n factorial. Very well. So let us define Taylor and Maclaurin series. Then try to write Taylor or Maclaurin series of some important functions. Taylor series. So if you have function f of x, you can use approximation, power series approximation, to write down the expansion for the function. So for function f of x, we can write it this way. The sum, the nth derivative of the function evaluated at a divided by n factorial x minus a raised to n starts from 0 to infinity. If a is equal to 0, then we can, instead of saying that we have a Taylor series, we can say that we have Maclaurin series. So Maclaurin series. F of x is the sum, the nth derivative of the function at 0 divided by n factorial x to the n starts from 0 goes to infinity. Okay, note that since we are approximating these functions using a series, we always have an error. To estimate this error, you can say that, hey, suppose the n plus 1 derivative of the function, if I take the n plus derivative of the function, it's less than or equals to a constant like m. Then the error function, or nx, or the remainder, is less than n divided by n plus 1 factorial times the absolute value of x minus a raised to n plus 1. Error, or the remainder of the difference between the actual function and its approximation. Let's go over one example. Question says, write Maclaurin series for exponential function. Maclaurin series for f of x equals to e to the x. So a Maclaurin series for a function is defined as the sum of the nth derivative of the function at 0 divided by n factorial x to the n starts from 0 to infinity. Let us write some terms of Maclaurin series, then we deal with our function itself. This is equal to the 0 derivative of the function at 0 divided by n is equal to 0, 0 factorial x to 0 plus the first derivative of the function evaluated at 0 divided by 1 factorial x to the first, plus the second derivative of the function at 0 divided by 2 factorial x squared plus the rest of the terms. The 0 derivative of the function is equal to the function itself. So this is just the function itself evaluated at 0. As 0 factorial is equal to 1. By convention, 0 factorial is always 1. So what is our goal? Our goal is to take our function f of x, e to the x, take its first derivative, take its second derivatives, and so on. We know that for function e to the x, the derivative of e to the x is equal to e to the x. It doesn't matter if you take the first derivative, second derivative, or third derivative of the function, it's always e to the x. So your function f of x, which is e to the x, has Maclaurin series, which is equal to f of 0, e to 0 divided by 1, x to 0 is 1, plus the second derivative of the function is also the first derivative of the function is also e to the x, so you get e to 0 divided by 1 factorial times x. The second derivative of the function is also e to the x, so when you plug in 0, you get e to 0 divided by 2 factorial times x, plus we can continue this process. The third derivative is also e to the x, we plug in 0, e to 0 divided by 3 factorial x squared. And so this is exponential, and this is exponential. Very well. So e to the x is equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus the rest of them. So you can rewrite this series as sum x to the n over n factorial, and you can say that hey, n starts from 0 goes to infinity. This is your Maclaurin series. Okay, another function. Suppose the question says, hey, write Maclaurin series for sine function. So your f of x is now sine function. sine of x. Very well. Okay. Sine of x is equal to sine at 0. So you have sine 0 divided by 1, x to 0 plus the first derivative of sine is cosine. So you get cosine 0 divided by 1 factorial times x plus the second derivative of sine, which is the derivative of cosine, minus sine. Then we evaluate that at 0 divided by 2 factorial x squared plus then the third derivative of your original function, which is now the derivative of negative sign, gives you minus cosine 0 divided by 3 factorial x to the third plus then the fourth derivative of the function, which is the derivative of negative cosine, which is sine. So you get sine 0 divided by 4 factorial x to the fourth plus the rest of the things. Okay, let us start simplifying the whole thing. You know that sine 0 is always 0. So you can quickly get rid of some of the terms. This is 0, this guy is 0, this guy is 0. What's left? Cosine 0, which is 1. So cosine of x is equal to cosine of 0, which is 1 over 1 factorial times x plus negative cosine of 0, which is negative 1 divided by 3 factorial x to the third plus, if you continue the rest of the terms, you can say it is 1 over 5 factorial x to the fifth plus the rest of it. So we can write sine x as the sum, power sum, negative 1 raised to n, x raised to 2n plus 1 divided by 2n plus 1 factorial. And then it starts from 0, goes to perfect.
One last question.
So now let us write Maclaurin series for cosine function. Very well. Okay. So cosine function, cosine of x, can be written as cosine 0 divided by 0 factorial, which is 1. Let me write down the whole thing. X raised to 0 plus the derivative of cosine, which is negative sine 0 divided by 1 factorial x to the first power plus the derivative of negative sine is minus cosine at 0 divided by 2 factorial x to the second plus the derivative of negative cosine, which is positive sine of 0 divided by 3 factorial x to the third. Let's write another term for you, plus the derivative of sine, which is cosine 0 divided by 4 factorial x to the fourth plus the rest of the terms. Very well, of course you can get rid of sine 0. Sine 0 is just 0. So what's left? The first term is left. Cosine x is 1 minus cosine of 0, which is 1, over 2 factorial x to the second power plus 1 times x to the fourth plus the rest of the terms. As you can see, here you have even exponents left. So you can rewrite cosine x as the sum. So x raised to 2n divided by 2n factorial and negative 1 raised to n. And starts from 0, goes to Maclaurin series for cosine function. Okay, now suppose you want to write, let's work with the cosine function, the same function. Instead of having Maclaurin series, you're going to have Taylor series. Taylor series for function cosine x at x equals to, let's say, pi. So your A is equal to pi. Very well. Okay. So the first term is your cosine function. Instead of having 0, your A is equal to pi. Cosine pi divided by 0 factorial x to the 0 plus. The derivative of cosine is minus sine at pi. Instead of having 0, you just keep substituting pi for your x. Divided by 1 factorial x raised to the first term. Plus, the derivative of negative sign is minus cosine at pi divided by 2 factorial x to, sorry, here we get x minus pi. Forgot to write this down. X minus pi to the first term. Here you get x minus pi into the formula 0 plus minus cosine pi divided by 2 factorial x minus pi to the second. Plus, you take the derivative of negative cosine, which is sine pi divided by 3 factorial x minus pi to the third, and you continue. So this is equal to cosine pi is equal to negative 1 divided by 1, and this is 0. This is raised to 0, which is 1. Then you get negative cosine pi. Cosine of pi is equal to 0, so you can get rid of this term. Cosine pi, sine pi is equal to 0, so you can get rid of this. Then another term that we have is plus negative cosine pi, negative 1 gives you positive 1. Positive 1 divided by 2 factorial x minus pi to the second. And if you write the next term is going to be plus minus 1 x minus pi raised to the 4th divided by 4 factorial plus the rest of the terms. So you can write cosine x, the Taylor formula, equals to sigma n starts from 0, goes to infinity, negative 1 to the n. Then here you have x minus pi to 2n divided by 2n factorial. That's the difference between Maclaurin and Taylor series. So we need to change this exponent. If you plug in 0, you get negative 1. So let's say this is n plus 1 or n minus 1.